Hello, welcome to the last lecture of the Glaciers course. I'm seeing last lecture. I'm not 100% sure yet. I might do an additional bonus lecture presenting a bit more. I work as a glaciologist and give you a bit more insight on what we do here at the Geophysical Institute, but that wouldn't be part of the curriculum in any way. There wouldn't be any test on that. This lecture, though, lecture 7, we'll have questions. There will be questions on that one in the tests, in the quizzes, and the final exam. And it is focusing specifically on the ice and the environment and how those two interact, climate change and all that stuff. But before diving into that, we'll do a quick recap of last lecture, where we saw the difference between erosional and depositional features. And here are two kind of summaries of what happens. If you remember, we said that when glaciers are flowing, if they flow fast, they will erode more than glaciers that are very slow. And it will also depend on what kind of rock is underlying the glacier. So if you have a lot of removable deformable till, that will be eroded much easier than solid hard bedrock by all the ice. So moraines are the very interesting features of glaciers because they can tell us a lot about them. Like terminal moraines can tell us about the maximum extent of a glacier. Medial moraines can tell us about how many tributaries there are in glaciers. They can also, I didn't talk about that, but medial moraine can record surges in the way that they loop and make super specific patterns about when a surge happened. And actually, I think I'm gonna show you a picture of that right now. So this is a picture of some looped moraines. Sorry, it's a bit blurry. But basically, you will have instead of having something that's pretty straight like it was on the previous image, whenever a surge happens, it can kind of disturb how the moraines were arranged on the glacier and make like super cool loops like that. And so basically you can count the loops that a glacier have and kind of guess the amount of surges it has been through in the last few years. And in general, the fact that we saw that rivers tend to erode mountains in a V shape and make like V-shaped valleys, while glaciers kind of always erode valleys in a U shape. And whenever you have a valley that is filled with seawater, it is a fjord. So yeah, I already talked a bit about that, how terminal moraines help us assess the maximal extent of some glaciers. Super precious because, as I said in last lecture, we can date the boulders and the rocks in those moraines or when they have been exposed to daylight. We can also measure how fungus grows on the rocks or what kind of vegetation is growing on the moraines and come up with a pretty precise estimation of for how long has this moraine been here, and so give us an idea about when the glacier was there for the last time. We also talked about ice coring on ice sheets and touched down on the many reasons why it's always better to drill a core site right on a dome where the flow is going outwards, and this is because of the vertical stacking of the layers of ice and the fact that the layers are pretty thick at the surface of the ice and gets thinner and thinner as you go deeper. So the important fact is that the deeper you drill and the faster you go through the layers because they get thinner. So in a way, you go back faster in time. And from the air bubbles that are trapped in the ice, we can recover the atmosphere during which those air bubbles were trapped. So it's literally a time machine into old Earth's configuration. And yeah, the oldest ice core we've recovered so far in the Epica ice core mission, that was Dome C in Antarctica. It was a European mission. That was 800,000 years. So we can go pretty far back in time and have really precise measurements of the atmosphere at that time. And the other very important thing, I hope you understood that process, was that that story about isotopes of oxygen and how oxygen, the molecules of oxygen the atoms of oxygen can have kind of two configurations, O18 or O16. The main difference between being that O18 is literally heavier than the atom of O16. Therefore, because it's heavier, it's harder to evaporate from the ocean, but it also precipitates the first when it's dumped by a cloud. And depending on the ratio of O16 over O18 in a sample of ice, it can also be a sample of sediment in the ocean, you can come up with ideas about how the climate was, because the more negative the ratio delta O16 O18 is, so the more negative it is, the colder the climate is, and the less negative this ratio is, and the warmer the climate is. So it's a very good indicator of the variations of past climates on our planet. And finally, we talked about records of carbon dioxide in the atmosphere, in past atmospheres, carbon dioxide being an excellent indicator of the temperature on the Earth, as well as the delta O16 O18. But it is, I would say it's more direct, it's more intuitive, in the sense that when we have very high levels of carbon in the atmosphere, we expect a warming to be associated with that. But usually those cycles of warming, cooling occur over thousands, tens of thousands of years, even if you look at that, 100,000 years. But the particularity of our time being that we as humans dumped a lot of carbon into the atmosphere that was usually trapped in the ground and kind of not in the system. And by releasing all that carbon, we are triggering warming that's already happening and gonna increase in the last centuries. So for as long as Homo sapiens has been walking on the Earth, there has never been levels of CO2 in the atmosphere as high as nowadays. If you go further back in time, like at the time of the dinosaurs, millions of years ago, when the Earth was nothing like it is today, we had much higher levels of CO2 in the atmosphere. We also had no humans living there. We had no civilization. We had no glaciers or ice caps. So the change that we are experiencing right now is really a big change compared to compared to the time during which there have been humans roaming on the Earth. So yeah, in the last century, we had a CO2 rising to an amount equivalent to coming out of an ice age. So here you have an ice age. Here you have an ice age as well, and you always have those what we called inter ice age periods where the Earth is usually a bit warmer, and we are right now in the inter ice age period, but maybe might have broken out of the loop of ice ages and stuff like that because we completely destroyed the ceiling of CO2 level in the atmosphere because of our human activities.